Saying we are live now. Yeah.
Hi, so our next speaker is Srujan Teja from IIT Kanpur. He's a PhD student at IIT Kanpur. He'll be talking on stochastic compositional gradient descent under compositional constraints. Uh, yeah, you can start.
Yeah. Okay. Good evening, everybody. So today I'm going to talk about this stochastic compositional gradient descent under compositional constraints topic. The brief outline of the topic is as follows. First, I cover stochastic gradient descent and stochastic compositional gradient descent as an introduction part. Later, I formulate the problem. Then I state the assumptions. Then I discuss two applications that have this particular structure. And then I finish my presentation by explaining the two algorithms that solve this problem. Okay, moving on. Yeah, let's consider a unconstrained stochastic problem as follows, which is an expectation function with respect to a random variable zeta. And when we want to solve this problem, the first algorithm comes to our mind is gradient descent. The gradient descent update step is well known. This one is the update step. And anyway, to implement this gradient descent algorithm, one has to find out the true gradient at every time instant, which is very difficult because the distribution of this zeta is unknown at this stage. So there is no way of finding this expectation value, the gradient of expectation value. So one possible solution is to use any estimator to this gradient, this true gradient, which is the stochastic gradient descent algorithm, which is well known and popular from past decade. So basically, the idea is instead of using true gradient, we can use an estimator of that gradient, which here in case is del of this function, gradient of the function calculated at this random sample zeta t. Well, so this is still a decent direction. However, the requirement to apply this SGD is the estimator of the gradient should be unbiased, which is very important. And the random variables that are revealed at every time instant are IID. It's simple and easy to use in many practical applications. There are many applications in machine learning problems in the literature. Okay, now consider a slightly complicated function where this expectation function is actually an argument to the nonlinear function f. F here it is nonlinear. So these are the details of that function. So as you can see, since f is nonlinear, the true gradient, this is the true gradient, but there is no way of finding any unbiased estimator for this true gradient, because to find an unbiased estimator, we need to know this expectation of inner function, this g function, which at this stage is completely unknown because the distribution of zeta is unknown. So one intuitive idea is we can have an estimator to this true gradient, but at the place of this inner function, we can use any as y tilde, which approximates this inner function. So this is called a quasigradient approach, which was first proposed by Dr. Mengdi Wang in Stochastic Compositional Gradient Descent Algorithms for Minimizing the paper, which was published in Mathematical Programming. So formally, the algorithm can be written as follows. So there are two variables. One is an auxiliary variable and one is the actual optimization variable. Well, the auxiliary variable actually tracks the inner function, average of inner function on with time. And while updating the actual optimization variable, we use this yt at the inner argument of the gradient of outer function. So this is the algorithm. And as I said, this was proposed in 2017, and there were many extensions after that. I've mentioned a few here, in which a finite sum case has been verified and proposed. An accelerated version of this algorithm has been proposed, and the nested versions are also have been proposed, where the expectations are involved in a nested loop functions. Note that this list is not limited. It still is an active area of research. and there are many problems are coming with this compositional structure. Yeah, now come to the problem formulation. So here the problem is more generalized here. So we have an objective function which is compositional, and constraints which are all stochastic and compositional, and we also have the deterministic constraints, and this is the more general version of the compositional problem. So I'm going to talk about this problem from this point onwards. So these are all the details of that problem. Well, basically they're saying the inner function can be vector, which maps from a vector to a vector, the both inner functions, and outer functions map from vector to scalar. So yeah, the setting is the distribution of zeta is unknown, so they are revealed sequentially and their IID. And for simplicity, I denote capital F of x to the objective function and capital Q of x to the constraint function. So yeah, how to solve this problem? So how to use stochastic quasi-gradients to solve this problem? And our aim is to find the first order algorithm to solve this problem. Okay, the assumptions are straightforward. The main assumptions, of course, are outer functions have to be smooth, and they also they should have bounded gradients, and they should be that meaning the outer functions are continuously differentiable. The inner functions can be non-smooth; they can have either gradients or subgradients, and strict feasibility is there. So we should be find out the solution to that problem. And the x is closed and compact. And other important assumption is this one: the positive part of the constraint function is bounded. So we have taken this problem over this set x, so it can be assumed. And yeah, remaining all are standard.
Srujan,
Yeah,
what do you mean by solve the problem? Any local optima is also fine with you, or
no. I want to find this extra.
you want to find the extra?
Yeah, no local optima. And however, the problem is convex. So yeah, that assumption is also there. I have missed it.
Yeah,
The
yeah.
problem is convex. Yeah. So
G is convex or G is which one? What all are convex?
so like whole this problem is convex. That means objective has to be convex and constraint has to be convex.
Yeah, but the objective F is there is also this expectation of Gx also inside it, right? So as a function
Yeah,
of
yeah,
is it
yeah. The
both in
function with respect to x is convex.
okay.
It's both objective and constraints. Okay. So now I'm gonna talk about applications. I discussed two applications. First one is a queuing theory application, which is designing optimal queuing systems. So this is a schematic. Let's assume a generic source which generates data continuously for a long time. It generates continuously data that follows Poisson distribution, and the arrival rate of this data is lambda. This comes to these packets will arrive at the queue, and then and a packet in a queue will be serviced when the transmitter at outside of the queue transmits that symbol to the receiver. Then it is said to be serviced. So we assume a simple encoder, that is a bit will be encoded as a symbol, and we can also, without loss of generality, assume the length of a packet is 1 bit, just for simplicity. So by saying that, the service time can be written as this one. So this B of P comma zeta is the capacity, the rate that transmitter can achieve. P means power. It's a power that is assigning to that symbol. And this is a Shannon's capacity. So we assume sufficiently long coherence time so that transmitter can achieve this Shannon's capacity. Yeah, so by saying MG1 queues, the service time distributions are general. So this is no longer, service time distribution is no longer exponential in this case. However, the incoming data distribution is Poisson, still Poisson. So yeah, by saying that this is the average queuing delay. This is a PK formula, well-known PK formula, which depends on the first and second order moments of a service time. So by plugging in these values, we can get these. This is an average queuing delay. By looking at this expression, we can see that this is non-linear function of expectations, right? So now the problem, now we can frame an utility function, which is a function of lambda and power p. So these two are the optimization variable that we want to find out. And we want to maximize the throughput. So this psi and var phi functions are user defined. It can be logarithmic function, and var phi can be a linear function. And also we have to minimize the queuing delay. That is our goal. So this is the utility function that we formulate, and we maximize this utility function. And the optimization problem is this. So yeah, it's more general, and we can have constraints, and we can have other constraints as well. I mean, we can move this to objective, and we can have constraint as queuing delay is less than or equal to particular value. It's up to requirement. So clearly, this problem is compositional structure and cannot be solved with normal stochastic gradient descent algorithm. Yeah, so but this intuitive formulation is missing in the literature, mainly because we cannot find the closed form expressions for these values. Although even we know the distribution of zeta. For example, if the channel, by the way, this zeta is a channel between transmitter and receiver. When the channel is Rayleigh faded, then zeta distribution is exponential. So for even exponential distribution, we cannot find closed form for this with respect to t as a function of t. So yeah, so there is only way. I mean, there is only way to solve this problem by using this SCGD update step. It's a first order algorithm. So this is the first application. And now for the second application, I took a machine learning application. So let's assume there is just a artificial intelligence assisted hiring process. So the goal is to select a candidate for a particular job. So that is the goal. However, the challenging issue is the training data is biased with respect to some sensitive attributes such as race, gender, and so on. For example, if you see the history, there were fewer females were hired in any company. So, but obviously the classifier should not exploit that historical tendency, and should give a decision fair to the both females and males. So that is the goal. So yeah, we cannot proceed with current models. So the model here is represented by this tuple, where X is a feature vector and Z is a decision label, whether a candidate is selected or not, and S is a sensitive attribute. Here I have considered two class sensitive attribute, but one can extend this idea to multi-class. Yeah, so several fairness notions have been proposed in the literature, but all these notions basically say that the decision process should be fair. But no matter how method you use, the classifier finally should reduce this risk difference value, which is basically saying on an average, number of selected candidates from the both parties should always be same. That means difference between those number of selected candidates in both groups should be less. That is the risk difference value. And this risk difference value can be simplified by using some Bayes rules. We can simplify to this point. Like this is explained in this paper. Yeah. So now the loss function is pretty standard. I have used logistic loss function here. One can use any other loss function which are used in practice. And the fairness constraints are this one. This risk difference should be less than or equal to tau, and also should be greater than or equal to minus tau. It should be in between minus tau to tau. So the tau is the allowed flexibility. So this classifier is allowed to have this much unfair towards the decision process. And in this application, in this example, I've taken all indicator functions are approximated by exponential functions, but one can use other approximations as well. For example, sigmoid function. So the constraint can be written as this. So this square thing will take care of this minus tau and tau. So this is one way of expressing this constraint. In this, clearly the square function is there outside of this expectation function, so it is non-linear. So we cannot solve using SGD. Yeah. Now, from this point onwards, so I have formulated problem and I have motivated two applications. Now the goal is how to solve this problem and how to handle the constraints. So that is our goal. Basically, there are two ways to handle a constraint. One is by penalizing the objective function, and other is by use of duality theory. So first approach is more conservative approach. Here I explain how to penalize the objective such that the constraints are handled. So for that, let's consider a different version of the original problem, where this is x gamma is equal to argument of fx such that qx plus gamma less than equal to 0. If you see, the solution x gamma is order of omega suboptimal because this gamma is positive and it's a positive quantity. If gamma is 0, then this x gamma is exactly equal to x star, the solution of original problem. And this gamma I've used to show you that it is possible that we can have zero constraint violation in an expectation. So by wisely choosing this gamma, I will show this at the end of this presentation. Yeah. So this is the constraint of the function. So I am finding a penalty function for this constraint, which is L. So this is the penalty function. I add this to the objective. So now the goal is apply SCGD step on this newly formed objective function, which takes care of both objective and the penalty and the constraint functions. So later we established bounds on both optimality gap and constraint violation, and we show that these upper bounds will go to 0 as number of update steps tend to infinite. And recall that the outer function should be smooth. So L has to be smooth. We should design penalty function such that it is smooth and also have bounded gradients. One such example is this one. If you see, if the constraints are negative, then the penalty is 0 because the constraints are satisfied. So we don't need to penalize the function. And if they're positive, they're penalized by square function. Square of the constraint value. And if we go beyond CL, then the penalty function is linear. Like this CL is upper bound for the positive part of the constraint function. If you recall, in assumptions, I stated that the positive part of the constraint function is bounded. Here that upper bound value is CL. So because since constraint cannot go beyond CL, we need not to have a square of penalty function. So I made it linear. So this Huber looking loss penalty function is smooth and also have bounded gradients. Yeah, now we have I have explained the penalty function. So now our goal is to find an update step. In a single update step, it should be able to minimize the objective function and the constraint functions, both constraint functions. Yeah, here this is not Q, this is L, this is typo. Basically, we are going in a descent direction of the objective function and also the descent direction of the penalty function. So yeah, these are the approximated gradients, the gradient estimators of this objective function and the constraint function. So similarly, the argument of the outer functions, we use approximations of inner functions, like as have been used in SCGD algorithm. So this y tilde and z tilde are the auxiliary variables that track these inner functions. Yeah, more formally, the algorithm can be written as follows. This y comma z are auxiliary variables that track inner functions of both objective and constraint functions, and use those tracking variables in optimization variable updates. Yeah, this is the main update. So here, if you see this update is going in decent which can be tuned. So it goes in the negative gradient direction of the objective as well as negative gradient direction of the penalty function, so that it does the both jobs. Yeah, so this is the algorithm. Now I state the final theorem. Let be the step sizes be constant or diminishing as follows: t power minus a minus b minus c, and abc values follow this condition. Then the objective error is always upper bounded by order of omega plus gamma. This omega is this one, order of t power a minus 1 and so on. And this is expectation. So expectation of positive part of the constraint is upper bounded by this quantity. Now, if you look at this quantity, this expression, if I choose gamma such that it is equal to order of t power minus c, t power c minus a by 2, then we can make this 0, right? This can be 0 by wisely choosing this gamma, so that we can completely nullify the constraint violation. So that was the main idea behind using this gamma suboptimal problem. Yeah, now we have to find a, b, c values such that these upper bounds are optimal. One such, yeah, these are the different choices of these a, b, c values. However, at max we can achieve order t power minus 1 by 12 convergence rate. Other one is order of t power minus 1 by 8 for objective, and order t power minus 1 by 16 for the constraint. For SCGD, for unconstrained stochastic problems, compositional problems, the convergence rate is order t power minus 1 by 4. It's minus 1 by 12, which is worse compared to these unconstrained problems, which is due to the constraints. Okay, so yeah. Now the proof approach. Proof is a pretty standard approach. It's similar to all the proof techniques that are used for other algorithms. First, we try to find an upper bound for this quantity, which represents the sequence convergence. If this is upper bounded by a small quantity which vanishes with the t tends to infinite, so that sequence will converge. And these are all the tracking errors. Like this g bar is nothing but the expectation of g of xt comma zeta. So to simplify notation, I have used g bar here. So this exactly represents a tracking error, which is upper bounded by a term which is a function of this one and the previous value of the tracking error, that has multiplied by some positive quantity, small positive quantity. Both will go to 0 as t tends to infinite, so it is also bounded. Now we try to find an upper bound for this quantity, and then from that we can find an upper bound for this quantity. Like this will be calculated by cancelling all the telescopic sums. Finally, this quantity will be upper bounded by some order of omega plus gamma, as stated in the theorem. So this is nothing but the first quantity is the objective error, and the second quantity represents the constraint violation, the positive part of the constraints. Yeah. So now, yeah, by adding and subtracting the fx star, it should be fx star and it should be fx gamma. We can because let's see, because here this lx hat is always positive, so the upper bound for this whole whole term will be hold for this term also, because it is positive. So, and this can be written like this, and fx star minus fx gamma minus fx star always be upper bounded by some constant into
sorry
gamma.
to interrupt, but I have 5 minutes left.
Yeah, okay, I'll finish it. Just 2-3 minutes. Yeah, so from this we can find upper bound for this objective error and constraint violation. This is the proof. And now if you go for primal dual method, so when we consider a constraint optimization problem like this, then this is the standard Lagrangian function, and this is the dual function, which is standard. And this is a stochastic dual descent algorithm, in which case you have to solve a Lagrangian function at each time instant for a sample realization, and then update the dual variable in ascent direction of the dual function. So, but this is difficult because at every time instant we have to solve a problem. So to solve that problem, there is another method which is saddle point algorithm, where actually we make augmented Lagrangian function which is strongly concave. We can make by making the Lagrangian function to strongly concave, which is done by subtracting this lambda square term. So we call this an augmented Lagrangian function. Now the saddle point algorithm is a simple update step, two variables. One is dual variable and one is primal variable. Basically, dual variable goes in the ascent direction and primal variable goes in a descent direction, because dual function is strongly concave and primal problem is convex. So the idea is these two variables will update and go reach to a particular point where strong duality holds, where the primal value and dual value both are 0, and that is the optimal point. However, this also requires these unbiased estimates for gradients. So this can be replaced with quasi-gradients. So this is the final formal algorithm for primal dual method, where all the gradient estimators we have used this use this tracking updates, tracking variables. Yeah, so this is a primal dual algorithm, and this is the theorem. So let be steps are diminishing. Here we have only alpha t, beta t, nothing else. Then the objective error is order of omega plus gamma, and the constraint violation is this one. And similar to the earlier theorem, we can choose gamma is equal to order of theta plus w, and we can make this constraint violation to 0. Yeah, now these w and theta values are as follows. Now we have to choose this a, b such that these errors, these upper bounds are optimal and equal. So this is the theoretical result. When we choose a equal to 3/4 and b equal to off, we can have the optimality error. The convergence rate of optimal error is t power minus 1/4, and the constraint violation is 0. The thing is, clearly the primal dual method has been improved upon the conservative method, and the convergence rate is reaching to the convergence rate of unconstrained problems. So which is the best we can do. So yeah. So primal dual method is much effective than the conservative method. And this is the proof approach, similar to the earlier thing. First we find upper bounds for the sequence convergence, and then tracking errors, and then by finding upper bound for this xt plus 1 minus x gamma square, we can have upper bounds for these two functions, which is a Lagrangian function difference between optimal dual variable and algorithmic dual variable, and optimal primal variable and algorithmic primal variable. So from this, by cancelling all the telescopic sums, we get finally we get the upper bound as an order of omega plus gamma for objective error and constraint violation. So from this we can prove the objective error, bound and objective error, and constraint violation. Yeah, with this I finish my presentation. Thank you. Please ask any questions.
So there have to be some other, so some of these inequalities here will involve concentration, right? For example,
Sorry?
some of these inequalities here will involve some kind of measure concentration. Right? For example, I think the last two blocks, the bottom right blocks.
This one.
No, yeah, that's one also. Yeah, that. So that probably requires some kind of conditions on these f and so on. So.
Yeah. The conditions are the assumptions that I have stated.
Okay. Mm-hmm.
Like, I mean, in this presentation, actually,
you always work under those assumptions.
Yeah. So I've stated assumptions in words, but yeah, we have upper bounds in terms of those constants. For example, a function is Lipschitz, then we have constant L. Okay. So all these upper bounds are the functions of those constants and the step sizes.
Okay. Mm-hmm. No more questions, then let's thank Srujan again, and thanks for the talk.
Yeah, thank you.